Hi everyone, I'm Wang, a PhD candidate in Dr. Li's group at the University of Pittsburgh. The topic of my presentation is effect of humidity on the molecular structure of ion liquid at the ion-liquid mica interface. Ionic liquids are made of bulky and unsymmetric ions, as the electrostatic attractions are dampened and the lattice structures are not formed. They are usually in liquid phase at room temperature. Ion liquids have many excellent physical properties such as low volatility, high thermal stability, and good tribological performance. The wetting performance of ion liquids on solid surfaces is important in many applications, such as, for example, ion liquids can be used as nanometer thick media lubricants for hard disk drives and micro and nano electromechanical systems, electrolytes for supercapacitors, and catalysis, which requires immobilization of ion liquid on particles. As a result, it is critical to understand and manipulate the molecular structures of ion liquids at the interface. Mica is often treated as the model solid substrate due to its atomic flatness, availability, and well-defined surface chemistry. Previous AFM and SFA studies show that the imidazolate ion liquids form extended layering under ambient conditions due to the electrostatic interactions at the ion-liquid mica interface. Other researchers, however, observed complete dewetting of ion liquids on mica under ultra-high vacuum conditions. In our previous study, we were aware of the effect of salt water on the layering, as water absorption on mica is inevitable under ambient conditions. We found that ion liquids form droplet structures rather than layering when confined on a heated mica. We hypothesized that the absorbed water on mica from humidity initiates the layering of ion pairs, while the molecular mechanism of the water-induced layering is still unknown. It has been reported by several groups that the mica surface needs to be in contact with electrolytes with high dielectric constant to be negatively charged. When water is absorbed in mica, potassium cation will be dissolved from the mica surface, so mica is usually negatively charged. On the contrary, ionic liquids are not effective electrolytes to dissolve potassium cation and induce the surface charging. To validate the mechanism, we first managed to control the relative humidity in lab using saturated salt solutions in a closed system. Relative humidity ranging from 7% to 99% were achieved with various saturated salt solutions. With the help of humidity control setups, we were able to use ATR-FTIR to categorize the amount of water absorbed on the mica surface under various relative humidity. We observed that, a significant impact of higher relative humidity on the water absorption. We then studied the effect of relative humidity on the microscopic wetting of liquids on mica by measuring the contact angle under various relative humidity. The ionic liquid uses BMFAP that has an imidazolate cation and a fluorinating ion. When the relative humidities are low, the initial contact angles are relatively high, and the contact angle is steady over settling time. When the relative humidity is higher than 50%, the initial contact angles are lower, and the time-dependent contact angles are close to zero. At lower relative humidity, the water molecules are strongly bonded to mica as Armstrong-level monolayer and bilayers. At higher relative humidity, more water molecules are absorbed, and they are more bulk-like. As a result, more potassium cations are dissociated at higher relative humidity. The more profound ion exchange between ionic liquid cations and potassium cations induce extended layering and a lower contact angle. We did TGA analysis to confirm that the microscopic wetting behavior of ion liquids on mica is not due to the evaporation of ion liquid, as BMFAP is thermally very stable at room temperature. We also knew that BMFAP is very hydrophobic by Carr-Fisher titration, so the effect of water absorption in BMFAP on wetting is very limited as well. To test the hypothesis that ion exchange between the liquid cations and potassium cations initiates the extended layering, we characterize the morphology of nanometer-thick BMFAP film confined on mica by AFM. The nanofilms were fabricated by deep coating as shown in this cartoon. When the relative humidity is low, we observe tiny droplets of ion liquids, or de-wetting. As the relative humidity increases, we started to observe more and more layering of ion liquids, especially when the relative humidities are higher. These AFM results demonstrate that the relative humidity significantly impacts the layering of ion liquids. As summarized in this plot, the molecular arrangement of ion liquids on mica are in line with the microscale contact angle results. In both cases, when relative humidity is lower, ion liquid has low wettability. When relative humidity is higher, ion liquid completely wets the mica surface instead. With all the results, we summarized the mechanism of the effect of relative humidity on the layering of ion liquid on mica. When relative humidity is lower, less water is absorbed on mica. The potassium cation stays on mica, so the nanodroplets are observed in nanoscale, and there is no change of contact angle with time in microscale. When the relative humidity is higher, more water is absorbed on mica, and potassium cations becomes mobile. Water absorption on mica enables the ion exchange of cations and initiates the layering of ion liquid ion pairs, and ion liquid complete wets mica surface in microscale. So the performance of ion liquids on mica can be tailored by simply manipulating the relative humidity. In conclusion, we report that the wettability of ion liquids on mica can be tailored by tuning the relative humidity. Water absorption on mica from ambient humidity enables the cation exchange and initiates the layering of ion liquid ion pairs. Under low relative humidity, ionic liquid droplets are observed in nanoscale, and de-wetting occurs in microscale. Under high relative humidity, extended layering are observed in nanoscale, and complete wetting occurs in microscale. We would like to thank the financial support from Advanced Storage Technology Consortium and ACS Petroleum Research Fund. Thank you all for listening, and please feel free to email me with any questions.